Hey folks, so we are looking at section 11.2 in our geometry class, and I want to go through some definitions with you. First definition to take a look at, please, is a curve. This is a figure that you can draw without lifting your pencil. So if you simply just start drawing whatever you want to draw, and as long as you don't lift up your pencil, what you have drawn is a curve. So that's what you've got here is a curve. Now, everything underneath this is different types of curves. So the first one is going to be a simple curve. A simple curve is a curve that does not intersect itself. So something like this would be a simple curve. It does not intersect itself. Next, we have a closed curve. A closed curve starts and stops at the same point. So in this particular case, if I have my curve, and if I start and stop at the same place, this is a closed curve. Next, I have polygon. A polygon is both simple and closed, but it's also made up of line segments. So if you'll notice the example over here to the right, this right here is a good example of a polygon. Notice it's simple, it does not cross over itself, it's closed, the end and the beginning are in the same place, and it's completely made up of line segments. These are called the sides. Next, you have convex. Convex, again, is a simple closed curve where any 2 points connected with a line segment stays in the interior. I'd like to point your attention down to one of these figures down below. Doesn't really matter where I put 2 points inside. Anytime I have 2 points on the inside of this particular simple closed curve, if I connect them with a line segment, that line segment is always going to be on the inside of my simple closed curve. Concave, however, is simple and closed, and it's not convex. So I have an example over here. I've already directed your attention to it over here on the right, and you'll notice that I've chosen 2 points on the inside, point F and point G, but when I connect them with a line segment, it goes outside of my simple closed curve. So this is where it is concave. Now, let's make this a little simpler. Concave is where you have something that looks like a cave on my figure, whereas convex has no places that look like a cave. Then I have polygonal regions. I could have the interior of the polygon, the exterior of the polygon. A polygonal region is where my polygon is in union or combined with its interior. So in this case, the polygonal region is not just the polygon itself where I have my 3 line segments, but it's also the inside of my polygon combined with that. So there's the polygon, the red piece is the polygon, but then when I include that with all of the stuff on the inside, that's going to be my polygonal region. All right, then if you'd like to jump down, please, to angles of polygons. The interior angle of my polygon is going to be an angle formed by any 2 sides of a polygon with a common vertex. Any 2 sides that have a common vertex. You can see here that I have an example of this. This angle number 1 is going to be an interior angle of my polygon. An exterior angle, this is the second example here. This is an angle formed by a side and an adjacent extended side. So angle 2 is an example of an exterior angle. The diagonal of a polygon is going to be any segment that connects 2 non-consecutive vertices, non-consecutive 2 vertices that are not side by side. So you'll notice here, vertices A and C are not next to each other. When I draw a segment between them, this is called a diagonal. Then I have congruent segments. Congruent segments are 2 segments that have the same length. Congruent angles are 2 angles with the same measure. hold this in your brain. We're going to discuss heavily the difference between being equal and being congruent when we come to class. I'd also like to direct your attention to these polygons. Equilateral polygons, this is where all of the sides are congruent. All sides are congruent. Equiangular polygons, this is where all of my angles in the polygon are congruent. Congruent polygons, this is where I have two polygons where the corresponding angles and the corresponding sides are all congruent to each other. And then lastly, regular polygons. This is going to be a polygon that is both equilateral and equiangular.